You can have this one.
I can?
It's yours.
Just all the good highlight was is during one of our field exercises, drill sergeant just like let loose on one female candidate or trainees because she was like trying. It was like 1 a.m. in the morning, and we just got done getting shot at. Like seriously, by these machine guns were like army crawling into this barbed wire.
Real machine guns?
Yeah, there's like 3.
They shot real machine guns at you?
Just directly at.
No, not directly at. Like there's a reason why you're crawling on the ground underneath the barbed wire. And then these massive barrels full of liquid propane that they'll send off so you couldn't hear anything. They're simulating RD.
Okay. Anyway, let's do these 2 questions. These are sort of these kind of like formula builder questions, I guess, where there's no numbers. So number 12 says if you have a block of mass m and it's sliding to the right across a floor with initial velocity of v naught. So it's traveling, it's going to be drawn like this. Okay. The coefficient of friction is mu, so here's some frictiony surface. There's the coefficient of friction between those 2 surfaces. How much time does it take for the block to come to rest? So we clearly need some kind of formula that relates the mass of the block, the coefficient of friction, and the initial velocity to a time value, right? So you might start a problem like this by saying, well, let's start by getting time involved right away. How will I find the time? Does anyone know the answer to that? Time would equal int.
Isn't it velocity?
Well, okay, let's. No, we're trying to go too fast. So okay, so think of the basics, right? So this is acceleration is change in velocity over the time, right? So if I solve that for t, it would be, what's the change in velocity in this problem if I'm going from v naught to rest?
From some value to 0.
That makes sense?
Yeah.
If I'm changing from this speed to 0, then the change in speed was that. Time, well, sorry, when I'm solving this, I end up with this. Is everyone okay with that?
Mm-hmm.
Okay. Now, we go, okay, I'm almost got a formula because I've got time equals v naught. That's one of my starting parameters. But there's no a given in the problem, so I can't have a in my formula. So how do I get maybe these involved? Well, let's draw the force diagram. mg, normal force is, right? What direction is the last arrow going to point? This way, exactly. So the friction is mu times the normal force. But yeah, because he's sliding to the right, that means the friction is pointing to the left to slow him down. And so how do I get the acceleration? Well, I have to write something like F net equals ma. What's the net force in this scenario? Mu mg. And then what happens? M's cancel out. So the acceleration turns out to just be mu times g. So let's say mu was 0.5, then the acceleration would be half of 9.8. If mu was 0.1, it would be a tenth of 9.8. So my formula, I guess, is T equals V naught over the A value, which is mu G. It's a pretty nifty formula.
Yeah.
Now, what do you notice about that formula? It's kind of interesting. It would actually defy, I think, common sense for a lot of people. Let's say it wasn't a block. Let's say I replace block with truck. A truck of mass m is sliding to the right across a road, maybe a slick road. No? No one knows what I'm talking about? There's what? The mass isn't in the formula. It's kind of interesting, right? I mean, it would make sense. I think a lot of people, if you said, well, which one would take longer to stop, a heavy block or a light block? They'd probably say, I think, what would you think they'd say? Probably the heavy block. They'd think the heavy block's going to go farther. But at least idealized, the mass shouldn't come into play. And why is that? Because, I mean, yeah, it's harder to stop more mass, right? It requires more force to stop a larger mass, but there's also, you get more friction if there's more mass. So those two effects tend to cancel each other out. Now, that's not to say, I don't know, you guys ever, who of you guys have like a pickup? Just one of you? Wow. Yeah.
What would you say?
How many of you guys have a pickup truck? Yeah, do you put snow in the back in winter?
Sandbag.
Or sandbag?
I mean, I just need to drive it.
You just don't drive it?
Yeah, just we have an extra vehicle, so I just drive.
Drives involved, man.
Yep. I put all my skis in it though. That's convenient.
In the truck that you don't drive?
No, in the van. I have all the seats and I like.
Anyway, that might, if you're wondering, why do people sometimes put snow or stuff in the back of their truck? Well, especially if it's a real-world drive, but even if it's four-wheel drive, you get that extra weight. You increase the normal force, you actually increase the friction. So if you're trying to like get going, you're trying to actually get extra traction, it can give you extra traction, but the extra weight would not necessarily make you, take longer to stop. If you were sliding. Okay. But again, I mean, just to clarify, this is of course an idealized situation where something is sliding across a surface. Of course, a heavy semi takes longer to stop than a small car because it's not sliding, it's relying on the brakes. And the brakes can only generate so much force. So if you're just saying, okay, these brakes can generate this much force, well, now of course on a large truck, the brakes are going to have the ability to generate more force than a small car, but still. A small car tends to stop a lot quicker because the ratio of like braking force to weight is a lot better than on a big truck.
Cars cut off semis, and then just like traffic stops, you just see the semis coming right in and just crush that.
Interesting.
No, that was Schaefer's thoughts.
Okay. There's a great video of Volvo. Volvo developed this like groundbreaking braking technology on their semis. There's cool videos where they show it's incredible how fast they're stopping. They're like,
How much weight behind them
huh?
though? How much weight behind them?
I don't know. That's a good question. I don't think they're like fully loaded semis, but just it's like the cab or whatever they call it. But it's coming to a stop like so quickly, and it's just like, I don't know. Maybe at the end of class we can watch the video if we have time. But
What if they have like a load full like ceramic plates?
well, yeah, if the truck is full, yeah, it's gonna take a lot. It's gonna be harder to stop. I think in the video I'm thinking of, it might actually just be like the cab. It might not have an attachment. They're just showing like it's this huge hulking truck, and you can see there's like it like throws the weight forward. Anyway, it's crazy because they show the perspective from the front of the truck, and they don't even hit the brakes until the car in front is like underneath the driver. Like the driver can't even see it anymore, and then the electronic braking system kicks in, and then it still is able to stop in time. It's pretty amazing. Okay, we'll watch it at the end of class. Just remind me. Okay, 13. This one is similar to this. Same setup pretty much. I mean, I can, I can pretty much redraw the same force diagram. mg, the normal force is mg. You guys remember what normal means? Perpendicular. Very good.
That was a better answer.
This is going to be really important later on to remember that when we start talking about putting a block onto a ramp. Because guess what direction the normal force points if you're a block on a ramp? Perpendicular to the ramp. You don't know what perpendicular is?
No, I would look at that.
Oh.
I know.
You know what perpendicular is. Okay, so there's my force diagram. Now this question just asking, same setup pretty much. What is, how far is it gonna go? Is basically the only difference. Okay. So I think it'd be fun to look at two different kind of approaches here. Let's do it the non-sneaky way first. What do you guys think the non-sneaky way is? If I want to relate mu, my initial velocity, to a distance. Notice that we're not involving time. So what's the non-sneaky way? Time-independent formula. Very good. So I'm going to use this formula. What am I solving for in this famous formula?
Distance, delta x.
Solving for that. And like, well, look, the breakdown is the same. What's the acceleration going to be on this problem? Mu g. It's the exact same net force, right? Same exact force diagram. Nothing's changed. So the acceleration is going to be mu g. Okay. And this expression, what am I going to end up?
I'm gonna have 0 minus.
Do not square.
Yeah. Well, here's where it gets interesting because, like, I mean, yeah, it'll be 0 minus this v value squared. And then over here, I mean, technically, what direction is this acceleration? Technically, it's negative. So I could say my acceleration is negative mu g. That's just because, I mean, I want to say that the displacement is positive, it's moving to the right. So anyway, what we end up with is v squared over. That's pretty neato. Everyone understand how I got from there to there, right? Does anyone know the sneaky way to do it?
Wouldn't the velocity just change in distance over time?
Kinda, yeah.
Don't we have a formula that was like v squared over 2g?
Yeah. Yeah. Well, what I'm thinking of is sort of kind of what Julie's talking about, which is displacement is average velocity times time, right? That rings a bell, right? Please say yes. Okay, so what I might do is say, well, if I'm going from a speed of v to a speed of 0, what's my average speed? Half of v. And how much time is this going to take? Well, we just solved that question, right? So the time it would have took was v over mu g. And if you multiply those, you get that expression. Isn't that neato?
That's a painful thing right there.
That's pretty neato. So, and this, yeah, so Julia, the formula that you referenced from before, which was talking about basically the max height. If you shoot a projectile straight up in the air with speed v, the max height it's going to reach is v squared over 2g. And we basically were able to do the exact same thing on that problem. Same, you can approach it two different ways, get the same answer. All right. Are there any more questions, like on just this general like friction stuff? There will be. We're gonna move on to springs. Springies.
This small, this thing could be so far.
Like one of those little kangaroo rats.
No, it wasn't a kangaroo rabbit, it was bigger than that, a very small rabbit.
Rabbit?
No, it wasn't.
Bunny.
I saw
a wild rabbit
No, it wasn't a chinchilla, it was like, it looked like a lemur, but smaller, and not the straight tail. No, it wasn't.
Okay. Okay. Springs. Okay. Springs have linear behavior, right? Or at least when we think of them as springs, in real life, in a second I'll show you this. This is more of an idealization, just kind of like what we talk about. Oh, ignore air resistance. We're going to always assume that springs, maybe I should say that. Assume, this is an assumption. This is usually a pretty good assumption. Unless you stretch the spring out really way farther than it's supposed to be stretched or squish it down way farther than it's supposed to be squished. A spring is going to, what do I mean by this linear behavior? Well, what I mean is if you start stretching a spring, so let's say this is the, how much, well, it depends on how you want to look at this, but say you go, this is the length of the spring, right? And this is how much force the spring exerts, right? You've all stretched a spring at some point, squished a spring. Every spring has a natural length, okay? So there's going to be some natural length to the spring, right? Because like this point, for example, would be if the spring is just chilling there. Let me grab a spring just to a little visual aid here. This one works. So this spring is already something like 10 centimeters long. Okay. Now, so there's no force. So the spring's not exerting any force right now. But if I stretch it out, right? If you've never held a spring before, you're welcome to try this one out. But when you stretch it, you're like, oh, it's exerting force. It is trying to pull itself back to its equilibrium position. So this point means this is the natural length of the spring, which a lot of times you'll call that like L naught or something. And then as you stretch it, the force increases linearly. Okie dokie? Yes.
You call it when a spring breaks or snaps in half. Excuse me.
What?
Spring break.
That's really bad. Oh, jeez.
hear that one recording, you can see like next time.
One more time?
Third time.
Yeah.
Okay. Now, now this spring, the way it's built, you can't really compress it because the metal's so close together. But a lot of times you can get a spring that you can squish, and so usually you can also do this. You can also make the length smaller than the natural length and get a force. So if you pull the spring, it wants to stretch back into its equilibrium. If you compress it, it tries to push back into it. So what we really are going to care about actually is think about the slope of this line. Don't you think the slope would be relevant? Anytime you have a line in anything science or math related, if there's a linear relationship, you almost always want to be talking about what's the significance of this slope. Okay. Who thinks they've got an idea for just in plain basic language? What is the meaning? What does the slope mean?
Change in force, so we're changing length.
Okay. That's a really good answer. I wouldn't say it's. Try to do plainer than that. Oh, like, I don't know, you're using a lot of big words there. Force, what does that mean?
Can it be just proactive bananas?
Banana pheromone steroids.
Maybe, I don't know. Julia is spot on, but you can say it in simple words. How strong is a spring? Right? A really strong spring, right? Imagine a really strong spring. Like say, the shock on a car. If you could somehow compress that 10 centimeters, you probably aren't strong enough. No, I don't think a human could do that. I don't know, I could be wrong, but
Yeah, have you tried Sam's broken shocks yet?
no.
See if you can go like this, man.
Yeah.
There's no way.
So you're a big man. I saw you do a push-up with one arm today.
Anyway, so a really strong spring, some industrial spring, right? 10 centimeters of stretch is going to produce thousands of newtons of force, right? So you're going to have a really steep slope. Your change in force responding to a change in length is going to be very big. So a big slope is going to be a very strong spring. This spring's not very strong. It's not super weak either. I mean, I can feel it, 10 centimeters. I have a different spring back here that's much weaker. Like this guy. The environmentalists will be really mad about this one. I ordered these little slinkies, and each one, for some inexplicable reason, was individually wrapped in plastic. I don't know why. It wasn't my fault. This spring, I can get a meter of stretch very easily with almost no force. I have to exert very little. I mean, if I just let it hang here, it stretches out on its own. Whereas this one is too strong to stretch out on its own. Did I ruin it the first time I used it? Wow. Good job, me. LOL. Springs. Anyway, it's a spring. To be honest. These things are so mysterious. They break they tangle up so easily. Sorry, let me get back on track here. I'll fix it later. Okay, so what do we call that? The change in force, that ratio of how much force do you get, how much extra force do you get for every additional length change. That's called K. That's called the spring constant. So every spring has a spring constant that tells you how strong the spring is. What do you think are the units of a spring constant?
Newtons and
Meter newton?
Newtons. Well, look at this. This is dividing. We'll talk about things that have the units of newtons times meters. But to get newtons times meters, you have to be multiplying the force by length. We're dividing force by length, so it's going to be newtons per meter. So that's the unit. The units of spring constant would be. So is this a dimensionless quantity? No, definitely not. It's how many newtons per meter. If you are some kind of imperial unit using Slav, you could maybe talk about, I don't know, could you go pounds per inch? Yes. Yes. Could you go pounds per foot? Sure. You can do whatever you want. You can make them whatever, as long as it's force per length. We're using SI units, so newtons per meter. Cool beans? Now here's the thing though. Most springs can't stretch a meter. So a lot of times you're going to be given your measurements in centimeters, and you just got to convert those centimeters to meters before you get your calculation. So let's do this first problem together. A spring. Do we have time? We're running out of time. Okay, lit. Speed run. Speed run. We'll just do number 16, and then I'll ask you guys to do 17 and 18 on your own. A spring is hanging from the ceiling with a 10-kilogram block attached. So 10-kilogram block, and the spring is 2 meters long right now. It's a pretty long spring, but it's possible. if we remove that block and replace it by a 16 kilogram block, how long is the spring now?
2.4 meters.
2.4 meters. Find the spring constant of the spring. So based on, first of all, I don't understand what the problem is talking about. Okay. So let's look at this. How much force how much spring force is that spring exerting, you guys think? Think simply. What?
Massive block.
Or,
Mass makes gravity.
Yep.
Yeah, so
MG.
98.
Does everyone understand that? You sure? Okay, gravity's pulling the block down with 98 newtons, mg. The spring must be exerting that much force to keep it in place. Okay. Now,
Oh,
what's up?
no, I was saying for the next step, would you find mass, or how many newtons that is, and you subtract that from the initial?
So now, with the new block attached, it's 16 times 9.8, which is 156.8 newtons. Well, hopefully we're all okay with that. And so let's take our new formula. Our formula says that the spring constant is how much an extra force was generated here. You just subtract them, right? So you go, what do you get here? 58.8. Newtons. So there's the change in force. That's how many extra newtons there were. What's the change in length? 0.4 meters. So Mr. Calculator divided by 4, or 0.4, sorry. You get 392 newtons per meter. And that's all you gotta do. That's not too bad, right? Pretty straightforward.
I got 147.
Oh, did I mess it up? Oh, you're right. Sorry, I had a typo. Yeah, that didn't make any sense. 147. Sorry about that. Thanks for fact checking me. Just testing you, obviously. Okay, 147 newtons per meter. Now, what does that mean? That means that theoretically you could stretch this thing forever. Every meter of extra stretch would increase the force by 147 newtons.
Wait, did you really stretch it forever?
No,
That's what you just said.
I said theoretically.
Oh.
so you have.
What really happens? Okay, thanks for mentioning that. So what really happens with any spring? I mean, I can ruin it here. I'll ruin a spring just for educational purposes. Okay, ready? I mean, at a certain point, you're stretching it, and this happens. Right? Now it's ruined. Okay? So what usually happens is you have this force versus length curve, and at a certain point, so let's say the curve's looking like this. At a certain point, you like max out that spring's stretchiness, and what do you think? Will it curve up or curve down? Didn't that spring get really strong, basically? Eventually, it's like a metal cable. So eventually it becomes like infinitely strong in a sense, until it snaps, I guess. So what happens is it actually cuts something like that. Does that make sense? But for, we're in intro physics, so if you were like a materials engineer, you might be really concerned with this domain. You might be really wondering, when does the spring end up like breaking down? But we're going to be focused entirely on the linear part. We'll be doing that.
I mean,